In the previous session, we have seen the electric field intensity due to an infinite line charge, right? We have derived an expression for that, the electric field intensity due to an infinite line charge. So during the process, what we have considered is we have considered two differential charges, or we can say point charges, and we have got the electric field intensity due to a point charge. Then we have integrated to for the entire length. Then we have taken the length and tends to infinity, limit of length tends to infinity. Then we have got the electric field intensity due to a line charge. Based on the same background, we can get the electric field intensity due to an infinite sheet of charge. Okay, so that's the next topic we have. We will see that today. Field of a sheet of charge. For this, we will consider there is an infinite sheet of charge. A sheet of charge, it's a surface, it's a sheet, a layer, a plane, right? It's a sheet of a charge. Whenever there is a sheet, it is there in two dimensions. That sheet or the surface is there in two dimensions. It can be in any two dimensions like xy or yz or xz, depending on where you place it. So in our consideration, we will consider an infinite sheet of charge which is aligned on the xz plane. Which is the xz plane? X axis is something which is coming out of the screen. Z axis is which is vertically upwards, right? So if you place it, that infinite sheet of charge will be like this. So this is actually a sheet which is perpendicular to your screen. Whatever you are seeing the screen, which is perpendicular to your screen. So it is difficult to draw it that way, so it is drawn like this. Okay, so this is an infinite sheet of charge. What we have to consider, the dimensions is infinite in the x-axis, it is infinite in the minus x-axis, infinite in the z-axis, and minus infinite in the infinite in the minus z-axis, right? So it is infinity in x and z-axis, and on y direction it is 0. That means it is lying at the origin in the xz plane, right? In the y direction it is 0. So here at the xz plane it is lying uh, perpendicular to your screen. Fine. So in this, we will try to get the expression for the electric field intensity due to this sheet of charge at a certain point P. Okay, at this particular point P, which is at a distance of D. This point P is at a distance of D from this infinite sheet of charge. Okay, so for this we will use xyz coordinates, that is the rectangular coordinates, since a sheet or a surface, a plane has symmetry when you consider rectangular coordinates only, right? So for that, we will consider x, y. So this y axis, the sheet of charge is perpendicular to the y axis, as we can see in this, right? The distance of the point P from the sheet is D. So what we will do is, this sheet is actually collection of a number of lines or line charges, right? So let the charge density of the infinite sheet of charge be rho s coulombs per meter. Okay, if the charge density is rho s coulombs per meter square, then the charge density of an infinite line charge will be rho s multiplied by dz. So if the elemental length in the z direction is dz, if you multiply the surface charge density with the length, you will get the line charge density, right? Units of surface charge density is coulombs per meter square. Unit of dz is meters. So unit of line charge density is coulombs per meter. That's why rho L is coulombs per meter. Yeah, consider what we will do is, we will consider two line charges which has charge density of rho L and rho L dash. Just like in the previous case of line, we had considered dq and dq dash as 2 point charges. Here we will consider two line charges, rho L and rho L dash. These two, both the lines are infinite in length in the x-axis, right? So this is in x-axis. This line is placed in x-axis, which is tending from minus infinity to infinity. So it's an infinite line charge. Similarly, this line in the negative x direction, negative z direction, this is also in the x-axis, along the x-axis, which is from minus infinity to infinity. This is also an infinite line charge, right? So the density, charge density rho L and rho L dash both are equal to rho S into dz. That is because rho S is the surface charge density of this infinite sheet of charge. Fine. So let the distance where these lines rho L and rho L dash lie in the surface be z and minus z. Okay, this is at in the positive z direction. This is in negative z direction. So the charge densities of these line charges that we have seen, it is rho s into dz. So surface charge density multiplied by elemental length in the z direction. So what we will consider is, we will consider the electric field intensity due to these line charges first. Due to these line charges which are symmetrical around the or about the origin. Okay, symmetrical means both the distances in the positive and negative z direction, that is the same. Okay, so let dE1 be the electric field intensity due to this charge rho L, line charge rho L. Let dE2 be the electric field intensity due to this line charge rho L dash, right? So this is calculated at a distance of d from this sheet charge, that is at the point P, which is at a distance of d. Due to symmetry, as we have seen in the previous case, the vertical components of dE1 and dE2, they are equal but opposite in direction. Of dE1, it will be in positive z axis. For dE2, dE2 will be in positive z axis. For dE1, it will be in negative z axis. So both are equal but opposite in direction. They get cancelled. But the horizontal components, that will be in the y direction. So both will be in the y direction. dE1 cos alpha, dE2 cos alpha. They will get added up. In fact, they will get doubled, right? Whereas vertical components, that is dE1 sin alpha and dE2 sin alpha, they are equal but opposite in direction. They get cancelled. So what we get is the sum of only the horizontal components. So dE1 cos alpha plus dE2 cos alpha, that is equal to dE, right? That's why the resultant or total electric field intensity at this point P, that is dE, will be equal to dE1 cos alpha plus dE2 cos alpha. Okay, so what will be the direction then? So we know that electric field intensity due to line charge, yeah, due to the line charge rho L, we have considered this in the previous case. Due to an infinite sheet of charge which has charge density of rho L, the electric field intensity is given by rho L divided by 2 pi epsilon r into ar cap, right? dE is, in this case it is dE1, that is rho L divided by 2 pi epsilon r into ar cap, where if r is the distance, okay, if it is in the radial direction. uh, we have seen in the previous case it was rho, because rho was the distance of the point from the line. Here the distance of the point from the line is capital R, that's why we have put capital R in this place. Okay, so now the resultant electric field intensity is direction. Okay, the direction will be in what direction? dE will be in, it is in ay direction, right? dE will be in ay direction, because y is the direction, that in rectangular coordinates y is the direction of, uh, yeah, because y, this sheet is perpendicular to y axis, that's why y will be the direction of electric field intensity. So then you can write this equation 1 as this one, right? So in place of dE1, okay, in place of dE1 we have rho L divided by 2 pi epsilon r, and dE2 is because of this line which has charge density of rho L dash, which is also equal to rho L anyway, that is rho L dash divided by 2 pi epsilon r cos alpha, and the direction of dE will be ay. Okay, direction of dE will be ay, that is y direction. So in place of rho L and rho L dash, we can substitute its rho S dz, right? Rho L is rho S into dz. Similarly, rho L dash is also rho S into dz. So we will substitute that. Since both the charge densities, they are equal, we get this term twice. So you can write this as 2 times of rho S dz divided by 2 pi epsilon r into cos alpha. That is in the next equation we have this 2 into this 2 and 2, they get cancelled. So what we get is rho S dz divided by pi epsilon r cos alpha ay cap. Now cos alpha, alpha is this angle, right? Alpha is this particular angle. So what is the cos of this angle? Cos of this angle is adjacent side by hypotenuse, that is d divided by r. right? Cos alpha is d divided by r. And from this right angle triangle, what is r equal to? R is the hypotenuse. So r is square root of d square plus z square, right? R is the square root of d square plus z square. So using this in equation number 2, we can write it like this: rho s into dz divided by pi epsilon. In place of r, I have square root of d square plus z square, and cos alpha is d divided by r, d divided by r. So again, r is square root of d square plus z square. If I put that, it is rho s into dz upon pi epsilon square root of d square plus z square, d divided by, in place of r I have written this, square root of d square plus z square. Now in the denominator, we have square root of d square plus z square multiplied by square root of d square plus z square, which in fact will become d square plus z square, right? It is just d square plus z square, and d from the previous, this I have written in a single term, rho s into d dz divided by pi epsilon into d square plus z square. So this is the electric field intensity at the point P due to two symmetrical infinite line charges, right, which are in the xz plane. Now we want to get the electric field intensity due to the entire sheet of charge, that is infinite sheet of charge. So to do that, we need to integrate this particular equation from 0 to infinity. Here the term is from 0 to infinity, not minus infinity to infinity. That is because whenever we have considered a line charge in the positive z axis, we have considered an equivalent symmetrical line charge in the negative z axis also. So if you integrate from 0 to infinity, so it will incorporate all the terms from 0 to minus infinity also, right? So that's why it is enough to integrate only in the positive z direction. So if you integrate this from 0 to infinity, so what do you get? So you can keep these unrelated terms to dz outside, right? So integration and differentiation, they get cancelled. So what we get is E, that is electric field intensity, that is rho s into d divided by pi epsilon into integration of dz divided by d square plus z square, right? So it is 1 upon d square plus z square with respect to z. The direction is A1. To integrate this, again, we need to make use of one standard integral. Okay, we'll make use of one standard integral, that is integration of 1 upon a square plus x square. That is given by 1 by a into tan inverse of x by a. Here, in place of a, we have d. In place of x, we have z. So this will become 1 by d tan inverse z by d, right? 1 by d tan inverse z by d. So that's why we get this rho s d divided by pi epsilon, and the integration of this is 1 by d into tan inverse z by d. Limits are from 0 to infinity. So if you substitute the limits of integration, you know, the first term will be tan inverse infinity by d minus tan inverse 0 by d. This term, tan inverse infinity by d, tan inverse infinity is pi by 2, right? You know, tan inverse infinity is pi by 2, and tan inverse 0 is 0, right? Tan pi by 2 is infinity and tan 0 is 0. So tan inverse infinity is pi by 2 and tan inverse 0 is 0. So this term is 0, and tan inverse infinity is pi by 2. So I will get this 1 by d into pi by 2, right? So in this term, this pi and pi, they get cancelled. Similarly, d and d, that gets cancelled. So what remains is rho s divided by 2 epsilon into ay cap. Okay, so electric field intensity is then given by rho s divided by 2 epsilon into ay cap. So this is the electric field intensity at any point due to an infinite sheet of charge. Here epsilon is the permittivity of the medium. If you consider free space, then this term will be epsilon naught. Okay, rho s divided by 2 epsilon naught into ay cap. The units for electric field intensity is again volts per meter, right? So what we need to consider here, see, the derivation you can do, it's a mathematical thing. Once you get the concept, you can apply trigonometry and get the expression for electric field intensity. But what you have to understand from this is, in this expression, there is no d. right? In the expression for electric field intensity, there is no d. No d in the sense the distance is not mentioned. That means electric field intensity due to an infinite sheet of charge does not depend on the distance of where you are finding the electric field intensity. That means this point P, if it is here, or whether it is very near to the surface, or it is at an infinite distance from the surface, from the sheet of charge, it doesn't matter, right? At any point, since the sheet of charge is infinite, right, the electric field intensity due to that sheet of charge is the same anywhere, right? It will be the same anywhere, but this is in the positive y-axis. Suppose we see consider a point in the negative y-axis somewhere here, then the direction will be minus ay. So it will be minus rho s divided by 2 epsilon into ay cap, right? In the positive is y-axis, anywhere you take, it will be rho s divided by 2 epsilon into ay cap. In the negative, it will be minus rho s divided by 2 epsilon into ay cap. So it is very clear that the electric field intensity due to infinite sheet of charge, it does not depend on the distance of the point where you are finding the electric field intensity, right? So this is all about the electric field intensity due to a sheet of charge or a surface charge of infinite area. Okay, so with this, we have completed this topic of electric field intensity. Okay, so next we have one more interesting topic in this particular module, that is electric flux. Okay, next topic is electric flux. This electric flux is actually the lines of force emanating from a charge, that is called the electric flux. The lines of force in the sense, whenever we consider a charge, say a point charge for example, it exerts some force on any other charge which is placed near to that, right? So when there is a force, it is indicated using some lines of force while we represent them. So those lines of force depend on the direction of those lines of force depend on what type of charge it is, right? The charge, it can be either positive or negative. Okay, suppose it is a positive charge, then the lines of force are moving away from that charge. Suppose it is a negative charge, then the lines of force are moving into that charge, moving inside that particular charge. Okay, so yeah, you can see it here. Electric flux is represented by the symbol psi. Okay, this is pronounced psi, psi, the Greek letter psi. P is silent. It is pronounced psi, and the unit is coulombs itself. The same unit for charge. The unit for electric flux is coulombs, and the symbol is psi. The electric flux sometimes is also called displacement flux. Okay, electric flux is also called the displacement flux. So what you can see here, the lines of force or the flux lines, this is positive charge plus q, this is negative charge minus q. So lines of force, you can see the direction, it is moving away, right? They start from the positive charge, and they end in the negative charge. If it is negative charge, the lines are moving into the negative charge. Okay, so this is the direction for negative charge, this is the direction for positive charge. So they start from positive and terminate into the negative charge. Suppose you consider a single charge plus q or minus q, you can write it like this. If the negative charge is absent, flux lines terminate at infinity. So these lines, they will be at till infinity, you will have this flux lines. So that means from the charge, in all the directions, you should imagine in 3D, okay, not just on this plane. In all the directions, you are having the lines of force moving away from a positive charge. So these lines, they are called the electric flux. If it is a negative charge, the direction is into the charge. Okay, from infinity, they will terminate or end on the negative charge this way. So these are the lines of force, right? So they are also called the electric flux. So when you consider, what we are interested is not just electric flux, but there is one more term, electric flux density. So when you consider the lines of force, are moving from a particular surface, lines of force moving out of a particular surface. Okay, so if you take lines of force per unit area, that is called the electric flux density. The electric flux per unit area is called the electric flux density. Okay, the term or the notation for electric flux density is d, D, capital D, because initially electric flux density was also called the displacement flux density. So that's why we use this term D, and the unit is coulombs per meter square, because unit for flux is coulombs and area is meter square. So it is coulombs per meter square. Okay. So to explain this electric flux density, we will take two concentric spheres, charged concentric spheres. Concentric spheres means they are balls. Okay, uh, two, you can say two spheres which are centered around the same origin, same center, which are having the same center. That's why we call them concentric. The inner sphere has a radius of r is equal to a. The outer sphere has a radius of r is equal to b. Okay, so both the spheres are metal conducting spheres, and in between those spheres we have an insulating material, or we also call the insulator as dielectric material. Okay, so what you can see is on the surface, on the outer surface of the inner sphere, there is a positive charge q. Okay, there is a positive charge q over this outer surface of the inner sphere. You can say, you can show it like this. It is completely charged. The total charge present is positive, it is q. On the inner surface of the outer sphere, inside the outer sphere, we have negative charges. It is negatively charged, and the charge is equal to what you have here, but it is negative. The polarity is negative. Okay, so completely you have negative charges spread over this. So you should imagine this as a ball. Okay, not a circle on this plane. You should imagine in three directions as a ball. Inside this there is negative charge inside surface, and inside that there is another ball. On the surface of that there is positive charges. The magnitude of both the charges is q, but their polarity is opposite. Here it is negative, on the surface of inner sphere it is positive. Radius of inner sphere is a and radius of outer sphere is b, right? That's why, yeah, there are two concentric spheres, radius is a and b. A is lesser than b, that means a is the inner sphere. Now you can see these lines, arrow marks, they are the flux lines. Okay, they are the flux. The direction of the lines of force, as we said, it is starting from the positive and ending at the negative. So since here you have positive, it is moving away from here. Since this is negative, it is moving into this, right? It is moving into this. It is ending here. Let plus q be the charge on outer surface of inner sphere, as we have seen, and minus q be the charge on the inner surface of the outer sphere. The electric flux density on outer surface of inner sphere. Flux density. What is flux density? It is flux divided by area. Okay, the flux divided by area. So what is the flux? The number of lines of force is equal to the number of charges. Okay, so always you remember, the flux is equal to the number of lines of force, that is equal to number of, or the total charge. So the charge is q. The charge is q divided by area of the surface of a sphere. What is the area of the surface of a sphere? That is 4 pi r square. Your r is a, right? 4 pi r square is the area of the surface of a sphere. In this case, r is equal to a. That's why it is 4 pi a square. Now, what is this? This is the electric flux density on outer surface of the inner sphere. It is flux divided by area. Flux is equal to the charge, that is equal to q, divided by the area of the surface of the sphere, that is 4 pi a square. And the direction is ar, that is radial direction. If you consider spherical coordinates, it is moving out, right? It is moving out radially. That's why the direction is ar cap. Now if you consider the inner surface of the sphere, inner surface of the outer sphere, inner surface of this outer sphere means where r is equal to b, the flux is minus q. The flux is minus q. The area of the surface is 4 pi d square. And what is the direction? Since it is minus q, the direction, since it is which is moving out, it will be in minus ar direction. The direction which is moving from this, when you are considering flux, it is from the area, it is minus ar. So if this is ar which is moving outward from the sphere, the direction which is coming into the sphere will be minus ar. That's why the flux is minus q divided by 4 pi b square is the area of the surface, and the direction is minus ar, that is inside, right? That's why the minus into minus, that will become plus. Again we have q divided by 4 pi b square into ar cap. Here r is equal to b. Now if you consider any point in between this a and b, in between both the spheres, if you consider any point which is at a distance of r from the center of the sphere, okay, if you consider any point which is at a distance of r from the center of the sphere, where r can be any point between a to b, we can have the electric flux density as the flux divided by the area. If you consider any point, if you form an imagine, if you consider a point here, if you form an imaginary sphere over here, okay, its radius will be r, small r, whatever it is, which is greater than a and less than b. So the area of that particular sphere will be 4 pi r square, right? So that's why the electric flux density at any point r from the center, which is in between a and b, that is equal to q divided by 4 pi r square into ar cap, right? So what we can observe is this is q divided by 4 pi r square into ar cap. This is electric flux density at any point which is at a r. This is due to the charge q, right? Electric flux density due to charge q at any point which is at a distance of r. Okay, so now we have the expression for electric field intensity due to point charge q, which is at any point which is at a distance of r. So we have already got that expression, right? That is q divided by 4 pi epsilon r square into ar cap. So what if you compare this equation q divided by 4 pi epsilon r square ar cap, this is electric field intensity, whereas this is q divided by 4 pi r square into ar cap. If you compare, what you can observe is there is only one difference, that is in d there is no epsilon, whereas in e there is epsilon, right? That's why you can write this relation, or if you try to get the relation between e and d, what we observe is e is equal to d divided by epsilon, right? If you divide the electric flux density by epsilon, you get this electric field intensity. Or in other words, you can say d is equal to epsilon into e, right? In free space, since epsilon is epsilon naught, we can write d is equal to epsilon naught into e, right? So this gives the relationship between electric field intensity and electric flux density. Okay, so these both the equations 3 and 4. This is for any medium. This is for free space where epsilon is epsilon naught. Okay, so one more thing you have, that is the electric field intensity. If you consider a general volume charge distribution, okay, if you consider a general volume charge distribution, what you have is for volume charge, the charge density will be rho v, that is equal to dq divided by dv, right? From this, we can write dq as rho v into dv. So if I integrate this, if I integrate, integration of dq will be integration of rho v into dv. So integration and differentiation of q. So it is q, which is equal to integration of rho v into dv, right? So we have seen this, right, while getting the equation for electric field intensity due to a volume charge distribution. So it is integration of rho v into dv. In place of q, it is q divided by 4 pi epsilon r square, right? In place of q, we can write integration of rho v into dv. This indicates volume integral. Okay, if I write v here, this indicates it is volume integral of rho v into dv divided by 4 pi epsilon r square into ar cap, where r is the distance at which you are finding the electric field intensity. Since d is equal to epsilon into e, right? If I multiply this with epsilon, the epsilon in the denominator gets cancelled. So this will be the expression for electric flux density for any general volume charge distribution. Integration of rho v into dv divided by 4 pi r square into ark. Okay, what you observe is it is not dependent on the permittivity of the medium. Okay, that means it is not dependent on the medium. Okay, it is not dependent in which medium you are finding the electric flux density. So now we will take another case. You consider the total flux is psi, okay, and the total distance from which the electric flux is moving out, that the sorry the total surface from which the electric flux is moving out, that surface area is S. Okay, normally we take surface area as a vector, right? Which is the direction of that particular vector will be perpendicular to the surface. Okay, suppose this is the surface S. If psi is the total flux moving out of this surface, we will consider a small surface ds. Okay, we will consider a small surface ds. This direction indicates the radial sorry the normal direction to this surface. So if d psi is the differential flux moving out of this differential surface ds, okay, if d psi is the differential flux moving out of this differential surface ds, then the electric flux density is what? It is d, that is equal to flux divided by area. The flux is d psi, area is ds, right? Flux is d psi, area is ds. If I rearrange this, d psi will be equal to d into ds. Since both are vectors here, we when you write multiplication, it should be specified whether it's a dot product or a cross product, right? Since both are vectors and the product is a scalar, it is obviously a dot product, right? The product is d psi, the flux is scalar, whereas d, that is flux density, is a vector, and the surface area is also a vector. So if you perform dot product on d and ds, we get this d psi. So d psi is d dot ds, that is the differential flux that is moving out of a differential surface ds. To get the total flux in terms of d and ds, what you can do is we can integrate this. If you integrate this, if you integrate this, you get this. Integration of d psi is psi, that is equal to surface integral, because it is with respect to surface. That's why we write it as the surface integral of d dot ds. Okay, so this is the expression for the total flux. The unit for the flux is coulombs. It is the same as unit for charge, that is coulombs. Okay, so with this, we have finished the basic concepts and all the concepts from the first module. But this is not all. What we have is, along with these concepts and equations, we also have some numerical examples based on this. Okay, so from next class, we will try to solve some numerical examples starting from Coulomb's law, electric field intensity, okay, and this electric flux density.